All right, look in your books and let me show you a theorem that you're going to like. Okay. All right. There's a theorem on page 84 that says limits of polynomials and rational functions. Now, I'm going to work it without this theorem, then I'm going to work it with this theorem. All right, page 84. All right. So that little box down under example 2. Limits of polynomials and rational functions. What I have taught you, if I asked you this, what's the limit of 4x squared minus 6 as x approaches 2? What's that answer? Well, now here's what you could do. I wouldn't, but here's what you could do. You could go make a table, like you did on that first section in this chapter, and get a guess off of what? The table. You could go graph this. What is this picture graph? What's 4x squared minus 6 going to graph? Parabola. It turns up. Is everybody with me? You could look at it there and look about when x is getting close to 2, what's y getting close to. Both of those would be guesses. Okay? But you could get good guesses with a table or with a picture, with a graph. Now, what if you want an exact answer? If you want an exact answer, what you could do is get a guess off of the picture and then do a proof. That proof would prove that your guess was exactly what? Correct. But that's a lot of trouble. So instead, I'm going to use those limit properties that you would talk about last time that you have for homework. Don't you have one that says that the limit of a difference is the difference of the limits? In other words, I can split this up and do the limit of the first one minus the limit of the second one. Now this one I can already do. This is the very first property I gave you. What's the limit of a constant? It's that constant. So the answer to this one, I already know what's the answer to that part. It's this. You can go ahead and do it if you want to. All right. I don't have one for like an ax squared. Now there are two ways to look at this. Some people see this as a b, like a number times a function, where b is your number. Some people see this as two different functions, where one function is a constant and the other function is x squared. I can follow either one of those. Now, I tend to think of it as this one, but mine's not more right than yours. So what I could do is use that property and pull that 4 out. Now, this one right here is that third property that I put on the board last time. So if I've got a variable to a power, this is y equals x squared, right? So on that parabola, every time x is getting close to 2, what's y getting close to? 4, because then it's squaring. And you told me that answer was a what? 6. So that's 16 minus 6, which is what? So that's working this problem right here using those properties. But this theorem on page 84 makes this way longer than it has to be. Look what the theorem says on page 84, that theorem 2.3, it says, if p is a polynomial function and c is a real number, then the limit of p of x as x approaches c is p of what? C. Now, here's the kicker. It only works if this is a what? Polynomial. Well, then you have to know what a polynomial is. All right, so let's go back and review algebra about a polynomial. Do you understand that a polynomial is the sum of algebraic terms with some conditions? And the conditions are that the exponents of the variables have to be whole numbers, not fractions and not negatives. So if I have something that looks like this, is that a polynomial function? What's the power on this one? 3. What's the power on that one? What's the power on that one? Now, there's not a variable here, right? You can think of it as x to the 0. So do you see that the powers on all of your variables are whole numbers? That's a polynomial. That's a polynomial. Why? Because what are the powers on your variables? Again, a what? 2. That's a whole number. What's that one? Now, E is a number we said that's pretty close to what number? 3. Now, it's just a number. Is that a polynomial? No. Why is that not a polynomial? Because what's the square root of x? How do you write that as a power? 1/2 is not a whole number. That's not a polynomial. Now, why is that not a polynomial? Because how do you write 1 over x? X to the negative 1. And again, that's not a whole number. So this theorem works when you have a polynomial. Is this one a polynomial? Yes. If you can guarantee me that it's a polynomial, what that theorem says, all you have to do is replace this variable with what? With that number. So I've got a 4, and then what's that S going to be replaced with? 2. Okay. So again, I get 4 times 4 minus 6. So again, I get what for my answer? 10. But I've got to know to do that it's a what? That it's a polynomial. Well, just substituting that number in is a lot shorter than doing all that. So if you know it's a polynomial, you now have permission to do it this way. Now, there's more to the theorem. Look what it says. If R is a rational function and C is a real number, all right, such that Q of C is not 0, then the limit of R of X is P of C divided by Q of C. Now, what in the world does that mean? All right, it means this. A rational function is a polynomial divided by another polynomial. So I've got to know what a polynomial is. So this theorem applies to 2 different things. It applies to just a polynomial, or it applies to a rational function, which is a polynomial over another polynomial. With a condition. As long as that denominator does not equal 0 when you substitute into it. Now, what do I mean by that? All right. What's the limit of 3x squared minus 4x divided by x plus 1 as x approaches 2? Now, what I could do is go back to those limit properties we went over last time. And I could do the limit of the numerator divided by the limit of the denominator. And then I could break that numerator up into 2 things, that denominator. So I could do all those different properties. Or I can say, wait a second. This right here is a rational function. Now, how do I know it's a rational function? Because a rational function is a what? A polynomial over another what? Polynomial. Okay, but I've got one more thing to check. And it says the same thing. You can just take this number and substitute it for that variable in a rational function as long as what? That denominator what? Doesn't go to 0. If it goes to 0, you cannot do it. I'll show in a minute what you will do if that happens. Okay? So what that means is now I've got permission to just take that x and replace it with the 2. Which is way less work than using those individual properties. Now, what do I do first? Multiply, power, subtract. What's mode of operations tell me to do first? Powers. So I'm going to have 3 times what? 4. So on that top, I've got what? 12 minus 8. What's that denominator? 3. So what's my answer come out to be? So if I've got a polynomial, I can just plug the number in and I'm finished. If I've got a rational function, I can just plug the number in and I'm finished as long as what? The denominator what? Does go to 0. So make sure we're clear about that. Here's what I mean. If I were to give you this on the test, I don't have permission to plug 0 into either of those. Why? Because when I do, what happens? That denominator goes to what? To 0. Now, here's the funny part. That doesn't necessarily mean there's not a limit. Because this one has a limit and this one doesn't. So when you try to plug 0 in there, I'm going to be pretty upset when I see you do that. Because why? You do not have permission to do that if that denominator what? Goes to 0. Okay? Now in a few minutes, we'll double check some things about this, but you've only got permission to plug in if it's a polynomial, or if you've got a polynomial over a polynomial and that denominator does not go to what? To 0. Now, there's another thing at the bottom of the page that makes life good. It's talking about the limit of a function involving a radical, so a root. Look what it says. Let n be, now what does n got to be? A what kind of integer? Positive integer. Not a fraction, it's got to be a positive integer. The limit below is valid for all c when n is what? Odd, and it's valid for all c greater than 0 when n is what? Even. And it says the limit of the nth root of x as x approaches c is the nth root of c. And it tells you that it's proved in the appendix. Now, what is that saying in English? It's basically saying this. What if you've got a radical? You got permission with that theorem at the bottom of the page to take this number and substitute in for this letter as long as you get a valid real number answer. So what happens when I take 2 and I plug it in for 3? What do I get? The square root of what? 5. Is that a real number answer? Then I can do that. But down here, I'm going to be in trouble. Why am I going to be in trouble when I try to do it here? Because I'm going to end up with the square root of a what? -4, and that's not a what? Real number answer. So I cannot do that. That is not allowed. Now look right here. When I take that 2 and substitute in here, don't you get the cube root of a -4? Is it okay to have the cube root of a -4? Yes. That's fine. So that's when they're talking about even and what? Odd. They're talking about this index number. When there's not an index number there, what's it understood to be? A 2. A square root. You might have 4th root. So if you've got an even root like a 2 or a 4, remember that radicand, that thing under there, has to be 0 or what? Or positive. But now if you've got a cube root, can't you have negatives under the root when they're a cube root? Because you can have cube root of negatives. The cube root of a -8 is just a what? -2. Because a -2 times a -2 is a +4, and a +4 times a -2 is indeed a -8. So what they're saying is, if you've got a root, you can also just take that number and substitute in as long as you get a real number answer. If you don't get a real number answer, it's kind of game over. The theorem doesn't apply. Okay? Now, they tell you the same thing on page 85 with your transcendental functions. Now, transcendental functions are the log ones, the e ones, the trig ones. You can take the number and substitute in as long as you get a real number answer. Okay? That's what it says. So if I give you something like this on a test, what's the sign of 3t over 2 as t approaches pi? Well, I've got this transcendental function. So according to that theorem on page 85, as long as this number is in the domain of this function, I can just take that and substitute in. So what am I going to replace t with? Pi. So I'm going to have the sign of 3 pi over what? 2. Now, what degree measures 3 pi over 2? Isn't that 270? Does sign depend on x or y? Y. What's your y value at 270 degrees? -1. Because when you're on that unit circle, remember the radius is 1. So if I'm down here, if I've gone all the way down here, that's the point 0, comma, -1. But now, do you understand that I would have been in trouble if this had been tangent? If that had been tangent, what's the problem with tangent right there? I'd have -1 over what? 0. That's not in your domain, so you don't have permission to do that. Okay? Now, here's what I want you to do for a minute. Okay, you try these for me real quick. those three real quick for me. Is this first one a polynomial? So can I take x and replace it with a -1? All right, so we've got 6 times the -1 cubed minus 5 times the -1 plus 11. So we just got to be careful with arithmetic. What happens when you cube a negative? Comes out negative, right? So this is going to be what kind of 6? -6, but it's going to be plus or minus 5. Plus 5 and then what? Plus 11. So what does your final answer come out to be? Everybody okay? Now, this one, have you got permission to plug pi in for x?
Yes.
That'd give me the cotangent of 7 pi over what? 4. Now, what quadrant am I in? Like, you need to take your calculator and tell me what angle is 7 pi over 4. Tell me what angle is that in degrees? 315. So what quadrant am I in? 4. Now, what is cotangent in words like sine and cosine? Cosine over sine. So think about x's and y's. So that'd be x over y, wouldn't it? What about the SIGNs? Is x positive or negative in quadrant 4? It's positive, but y is what? Negative. So when you take a positive and divide by a negative, what's the final answer going to be? Negative. Okay. Now I've got to find the reference angle. Now, I'm in quadrant 4, you told me, correct? So if I'm in quadrant 4, that reference angle is 360 degrees minus my given angle. All right, you told me that my given angle was 315, so what's my reference angle? 45. Now, the lovely thing about when things are written in radians, that's your reference angle. What's pi over 4? 45. That's the advantage of having things written in radians. So again, in my mind or on paper, I'm going to sketch out that 45, 45, 90. Aren't your legs 1 and 1? What's your hypotenuse? Square root of 2. Now, I want the cotangent. What's cotangent in words like adjacent, opposite, and hypotenuse? Adjacent over what? Opposite. So 1 over 1 is just, so I get a -1. Everybody okay with that? Okay. Look at this one. Is this a polynomial function? Yeah. A constant is also, that's the same thing as like 6x to the 0. So it's a polynomial. So I'm good. So when you take 0 and plug it in, what do you get for your final answer? Which is negative what? 1. Is everybody okay? Now, let me caution you about something though. I still need you to know those limit rules that I wrote on the board last time, because I can force you to use them on a test. All right? And the way I could force you to use them on a test is to give you a problem like this. The limit of f of x as x approaches 3 is 6. And the limit of g of x as x approaches 3 is a negative 2. Do you know anything about f of x? No. So you don't know if it's a polynomial or a radical. You don't know what it is. All you know is the limit of that function. As you get close to 3, the answer is what? 6. So I could say, find this for me. Find the limit as x approaches 3 of 4 f of x minus g of x divided by, g of x squared or something. Is everybody with me? Well, now I can't just go plugging numbers in because there's not a number what? To plug into. So I've got to go back to those limit rules, all right? One of your limit rules, the limit of a fraction, and the limit of the top over the limit of the bottom. Okay. Then again, I don't know what 4 times f of x is, so I can't just go plugging in a 3 there and saying 4 times 3. I'll fuss it. The only time you can plug in a 6 is when you have the limit of f of x approaches 3 with nothing in front of it. But I've got a theorem that says, what can I do with that 4 if I want to? I can pull it out. All right, and then I can separate those. And then I've got the last theorem, I don't know if we went over there, says I can take that limit and slide it in there. And then square it. Now I can go use what they told me. I know what the limit of f of x as x approaches 3 is. What's the answer to this thing? It's what? 6, isn't it? In other words, I can't write down a 6 until I see this exact thing right here. And sure enough, there it is. So I know that thing is the 6. So I can replace that thing with a 6. And again, I can't go writing down a 2 until I see this exact thing. But there it sits. So I can write in a 2. And then again, I can't go put in this 2 unless I see that exact thing, and there it sits. So I've got a 2, and I can square it. So I can force you to go back and use those limit rules. So don't think that just because you've got these shortcuts now that those limit rules are obsolete, because they're not obsolete. All right? So what will my final answer be? You tell me. What's the numerator going to be? 20 what?
Oh, is the 2 supposed to be negative? They're supposed to be a negative.
Not negative 2. All right, let's make that a negative 2. So that's going to make it a what? Plus a what? Positive. So I'm going to have what on the top? 26 over what? 4, which is going to reduce to what? 13 over what? 2. So there are ways for me to write problems that will force you to go back and use those limit properties. So don't just ignore them.
If we can use those properties, can we go back and check it through?
Yeah, absolutely, absolutely. And that's always a good idea. You get the same answer either way. That's exactly right. Okay? Now, let me show you what happens when those fail you sometimes. Now, sometimes there's ways to play algebra to make your life better, and sometimes there's not. Okay? Now, what do I mean by that? Let's go back to one that we had on the board a minute ago. I don't remember exactly what it was, but I think it was something like this. Right? Is that a rational function? Is that a polynomial over another polynomial? So why can't I just take the 2 and plug it in? Because that bottom goes to 0. Now, when that happens, sometimes you can do something to fix it, and sometimes you cannot. So they're kind of what you might think of, I want to use the word trick, because trick isn't, they're manipulation. They're an algebraic manipulation. Can you factor that numerator? What does it factor into? X plus 2 times what? X minus 2. So what do you think I'm about to do? All right, I'm going to divide the x minus 2's out. Now, we're going to talk about that in a second. Because you can't always do that. So I need you to think through, can you or can't you? Okay? So what's that going to leave me? That's going to leave me the limit as x approaches 2 of what? X plus 2. Is that a polynomial function? Yeah. So if it's a polynomial function, can I take the x and replace it with the 2? So what does 2 plus 2 give me? 4. Sometimes factoring helps. Sometimes it doesn't. Okay? Now, but you got to write, I need to make sure you understand the mathematics. Why can you just divide those things out? What do you really, see, I don't like the word cancel. Here's why I like the word cancel. When you divide them, what are you really saying that equals? 1. So any number divided by itself is 1. Is that true or false? It's false. Why? 0 divided by 0 is not what? 1. We don't know what it is. It's indeterminate. Talk about that a good bit in Cal 2. Okay? So here's the kicker. You can only divide those out if you can guarantee me that you didn't do this. Call that 1. So how do you know that x minus 2 divided by x minus 2 isn't 0 over 0? There's something in this problem that guarantees you that's not that you're okay. But you got to be able to tell me on test what it is. When's the only time that x minus 2 over x minus 2 would be 0 over 0? If x was what? 2, right? So what in this problem guarantees you that x is not 2?
Never touches.
Yes. This does. What does that mean? We talked about the very first day with limits. What does x approaching 2 mean? I get what? Closer and closer, but what? I never get there. So you're going to have to write me a note on your first test that says x approaching 2 guarantees that x minus 2 is not what? 0. Because a lot of times I'll have somebody just crossing stuff out all over the place. Somebody did it on the review sheet. Somebody always does it on the review sheet. Now, what do I mean by that? See, when you do that, when you don't think it through, your answer's not right a lot of times. Remember, I don't know what the problem was. Remember you had something like 2 sine squared theta minus sine theta, I'm just going to make it simple, equals like 0 or something. You can't just factor out a sine theta and then divide this side by sine theta and divide this side by sine theta, and those go out and you have 2 sine theta minus 1. You can't do that. And the reason you can't do that is you cannot guarantee me that sine theta isn't 0. So you just lost some of your answers when you did that. So when you start dividing stuff out and making it go away, and what do you think of canceling out? What you're doing is you're saying that that equals 1. And so you got to stop and think, okay, any number divided by itself is 1 except 0 divided, okay, I'm cool. I'm not crossing 0 divided by 0 and putting a 1 there. So you got to show me that you thought it through. Now, sometimes factoring doesn't help. Now, what do I mean by that? I mean, I gave you another one right below there that said something like, I don't remember exactly what it was. See, I can't factor there. Everybody with me? Or what if I gave you this? You can factor. I'm going to get x plus 2 over x plus 2 and what? X what? Minus 2. Now, I'm good to go there because when's the only time that's going to be 0 to 0? When x is a what? Negative 2. Well, it's nowhere near a negative 2. What's your x getting close to? Positive 2. So, you know, x getting close to 2 guarantees me I'm not anywhere near what? Negative 2. But here's my problem. Then I end up with this. Did I help my situation at all? No. So sometimes this technique works, and sometimes what? It doesn't. So what happens when it doesn't work? When it doesn't work, here's what I call it. In case of emergency, break glass. A guess is better than nothing, right? And if your guess is correct, life is great. So if you get lost, like take your graphers out for a second. Do you see this function right here? I want you to type it in your y equals key. Y equals x squared minus 4 over x minus 2. Now, when you type it in, you better put that numerator in a parenthesis and you better put that denominator in a parenthesis or you're not going to have the right graph. So I've got an x squared minus 4 in my numerator in a parenthesis divided by, I've got an x minus 2 in my denominator. Now, I'm going to go make a table. Now, I'm lazy, so I'm going to make the calculator make my table. So I'm going to go to second graph. That's my table. In other words, I'm going to go make my table. I'm just going to go second window to make my table set. You see where it says table start? So again, to be efficient, I'm just going to start it with 2. And then I'm going to go up by that delta table means what do you want the table to change by? Maybe I'm going to go up by 0.1 and hit enter. Now go look at your table. So second graph, that table. Is everybody with me? See if I can type mine in correctly. Oops. So did you get like a 2.1, you have a 2, you have a 2.2, a 2.3, everybody with me? And you can just copy those values down here for me. Now, I also need to know what's happening on the other side, like 1.9, 1.8, and so forth. Can't you just scroll backwards? Is everybody okay? Now, what is your answer like it's getting close to both times? 4. So you might guess 4 from your tables. Everybody with me? Now, try this one. Try to make this one on the table and see what happens. See if you're getting close to anything over there. That time, are you getting close to anything? You're not, are you? Now, some people would rather look at the graphs. Now, let me make sure we're clear about this. I want you to go back and graph this one with your machine. Because most of your machines are not going to graph it correctly. All right, did you get that picture on your graphers? It's not right. What's wrong with it? This is the graph of x plus 2. What do you know x cannot be in this function? We just talked about it. What can x not be in that function? 2. That's the graph of that function. It's a line with a hole in it. That's what that one is. When the hole is filled in, it's that line. So are these graphs identical? Are they the same graph? True or false on one of my tests? What? False. They're not the same graph. They're almost the same, but let's tell the copy we're almost going 7. You with me? Almost means no, I was not. This is a solid line. This is the same solid line with a what? With a hole in it. There's only one time they're not the same. When's the one time they're not the same? When x is what? 2. But see, this guarantees you that you never get to what? You never get to 2. So that's why you got permission to work this problem instead of what? Instead of that problem. Because as long as you're not at 2, the graphs are what? The same. Now, what does this graph look like? Doesn't it shoot up on one side and shoot what? Down on the other side? So you're not getting close to the same thing. You got an asymptote at 2, don't you? So it's shooting up on one side and what? Shooting down on the other side. The answer to this one is does not exist. Now, how would you, because it's going to say on your first test, you got to defend your answers. So how can you defend your answer to this? You can either make me a table and show me that these numbers are getting smaller and these numbers are getting bigger, or you can show me the graph. That would be your defense of your answer to what? Does not exist. But it's not does not exist because you get 0 on the bottom. Because you get 0 on the bottom here if you do have a limit. But that's what I mean by in case of emergency break glass. If you get stuck on a test, you can always make a table or look at the graph and get a guess. Now, If the answer is something like 4, you could probably get exactly the right answer with a guess. If the answer is 111, I doubt you're going to get exactly the right answer. So you can't just make tables and look at graphs for all the problems. Is everybody with me? Now you'd get partial credit for giving me a decimal approximation probably for 111. So you'd get some credit, be like, well, your answer's close, but it's not exactly right. So the theorems get you the answers that are exactly right. Is everybody with me? All right, let me show you another one that sometimes comes up besides factoring. And again, this is one of those techniques that once you see it, then you remember to do it. It goes back to that idea of those radicals. All right, so suppose on your homework you end up with a problem like this. Let's see. Suppose you have a problem like that. Now, if I've got a problem like that, why can't I take 0 and just plug it in for x? Because that bottom goes to what? To 0. Well, now my trick before was to try to factor it. But this time factoring what? Not going to help. And then I noticed something, I've got a root. Well, there's something I learned in algebra that sometimes is helpful to get rid of roots. And it's called multiplying by the conjugate. Do you remember what a conjugate is? A conjugate is exactly the same thing with the operator change. So it's going to be the square root of x plus 1 plus 1. All right. If this were a minus, what would that one be? A plus. It wouldn't matter whether there were 2 roots or the number was here and the root was there. But now if I multiply the top by that, what have I got to do? I got to multiply the bottom by that. Now, here's kind of the trick, so to speak. Look at the original problem. On the original problem, where was your root? In the top or the bottom? The what? Top. Wherever your root was originally, you need to multiply that out. The other one, do not multiply it out. Now, what do I mean by that? Multiply these two things. On your paper. So use that distributive property of multiplication over addition and subtraction and multiply that out and see what you get when you do that. What do you think of as FOIL? I don't like that term, but I get it. What happens when you multiply the square root of x plus 1 times the square root of x plus 1? You just get what? X plus 1. Now, when I do this root times 1, I just get that root. When I do this root times this minus 1, don't I get minus that root? So what happens to my inner terms? They go away. And then I've got minus 1 times 1. So does everybody understand when I multiply that numerator out, this is what I got? Now, I'm not going to multiply the denominator out. I'm just going to write it down. It's this denominator times that one. Now let me reiterate, how did I know which one to multiply out? Where the root was what? Originally. Because sometimes it's going to be on the top and sometimes it's going to be on the bottom. Okay? So wherever the original root was, multiply that one out and do not multiply the other one out. Now look what happens when I do that. What happens to these ones? They go out and leave me what on the top? X. I'm not multiplying this out, I'm just writing it down. Now do you see why I didn't multiply it out? Because what can divide out now? Now again, how do you know that's not 0 over 0? What guarantees you that's not 0 over 0? So you're going to tell me x approaching 0 guarantees that x is 0. So I know I didn't just cross that 0 and 0 and call it 1. Now, what I'm left with is not pretty. It looks pretty nasty. I've got a 1 over the square root of x plus 1 plus 1. But I can take that 0 and just do what? Why is it okay just to sub in now? Because when I sub 0 in there, what's that going to be the square root of? 1, right? Plus that 1. So what's my answer going to come out to be? Just what? 1/2. So sometimes multiplying by a conjugate helps. Sometimes it does, sometimes it doesn't. Okay. Now, what you're going to have for homework is a whole bunch of limit problems. Sometimes you can just take the number and just plug straight in. When you take the number and you just plug straight in and it works, life is great. When you try to take the number and you plug it in and it doesn't work, you've got some tricks to try. One is try factoring and see if factoring helps. Sometimes it does what? Sometimes it doesn't. Okay? So your other option then is if it's a root, you can multiply the top and bottom by that conjugate. But see, if you go multiplying this bottom out, you're going to lose something. You see why you don't want to multiply that bottom out? Because then you probably won't notice that you can divide that x out. So if you multiply by the conjugate, only multiply out where the root was originally. If you get lost or none of your techniques work, what are the two things you can always do to get a guess? Make a what? Make a table. Now, some people work better from the table. What else can you do besides make a table? Look at the graph. So if I give you something simple like this, so you're kind of stuck. You can't take 0 and plug it in, right? You can't factor it. There's nothing to factor. There's no root. There's no conjugate. So I'm left with, I'm going to go down here and make a table. Now, if you put 0 in there, the world ends, right? What happens if you put a 1 in there? What comes out? 1. If you put a 2 in there, you see what I'm saying? But I'm trying to get close to what number? 0. So I'm going to make the table, and I'm thinking about 0 and 1 and negative 1. So maybe I get like a negative 0.1. Maybe I get a negative 0.01. Maybe I get a negative 0.001. Is everybody with me? Same thing over here. Maybe I get a 0.1. Maybe I get a 0.01. Maybe I get a 0.001. Now, what number is that? Negative what? 1/10, right? So aren't you going to have a positive divided by a negative? Which is going to make it what? Negative. All right? So I've got 1 divided by 0.1, but it's negative. Now, you can do it with your machines or just use common sense. Isn't that a negative 1/10? So that's a 1 divided by a negative 1/10, which is the same thing as 1 times a negative what? 10 over 1. So what's this answer? Negative what? 10. You know what that answer is gonna be? Negative 100. You know what that answer is gonna be? Negative 1,000. Are you getting closer to anything coming this way? But you gotta come both ways. Same thing. If you use a positive 1/10, aren't you just gonna give a positive what? 10. And a positive what? 100. And a positive what? 1,000. So this would be your argument for what? Does not exist. Or you might write down, there is no limit. Now somebody else might look at the graph. All right? When I've got a positive 1/10, this thing is all the way up to 10. In other words, it shoots up this way. Over here, it's going to shoot down that way. Is everybody with me? When you graph it with your graphers, or if you graph it by hand. At 0, are you getting close to anything? So somebody else, this might be their argument for why the limit what? Does not what? Exist. But you can't just write down does not exist. I have to have some justification for it. Either you looked at a picture or you looked at a table. Question.
If I chose like to use the graph on the test as my justification, do I have to even write anything like because they're okay?
Now we'll tell you this, I do need some tick marks with some numbers on the graph. Does that make sense? So I do need to know, kind of what graph you were looking at, what these going up by 1s, 10s, 20s, 10s, what you were going up by. Now, you can do this when you can work it the other way, and as long as your answer is exactly right, you get full credit. It's just I'm going to make sure that some of the answers are things like the square root of 3 and 1/11, so that you can't just make tables or just look at the graph and get the exact answers all the time. Okay? Now, we've got one more thing to cover in this section, but I want you to play with these first before I show you the other one, because it's a trig thing, which always freaks y'all out. Okay? So what that means is Monday, what is today, Wednesday? Monday of next week, we're going to cover the last material that's going to be on your first test. So your first test is going to be a week from that, which is like what, the 21st, I think? Monday should be the 14th, so 7 days later should be the 21st. So, well, you got almost all the material on your first test now, okay? So part of your homework assignment is going to be kind of to start studying for that. Now, make sure we're clear.